Welcome to this episode of Eureka. We are going to have a very wonderful, very engaging conversation with Dr. Kapil Paranjape.
Thank you.
He is a professor of mathematics at the Department of Mathematical Sciences at Indian Institute of Science Education Research, IISER, Mohali. Before we continue this conversation, let's look at his brief profile and then the conversation will continue. Keep watching Eureka.
Professor Kapil Paranjape is a passionate and award-winning mathematician who is also well known for his work in algebraic cycles. Dr. Kapil Paranjape is currently a professor of mathematical sciences at IISER Mohali. Dr. Paranjape has joined the Indian Institute of Technology, Kanpur, where he pursued a 5-year integrated master's program in mathematics and graduated with first-class distinction in 1982. His research interests are centered on geometry, more specifically on algebraic geometry and the study of algebraic cycles. He has also made highly significant contributions in connecting Hodge theory to the study of Chow groups. Dr. Paranjape has been awarded with various national and international recognitions. Noted among them are the Shanti Swaroop Bhatnagar Prize for Science and Technology in 2005, the highest science award in India in the mathematical sciences category, and a J.C. Bose Fellowship in 2010. And recently, he has been elected a Fellow of the World Academy of Sciences of TWAS.
Thank you. It's been a very wonderful opportunity and we'll sure have a very engaging conversation. Though mathematics perhaps people might think that it'll put off them. I'm sure after this program, they are going to say that why we hated or we felt maths as something difficult till now. So let me start with a very, very simple question. Your area of work for which you are known and your area of research is what is called as algebraic geometry.
That's right.
There are two words, algebra and geometry.
That's right.
So how do we understand these two words in a very simple way? Then let's go build by step. So how do you say algebra?
So algebra is the subject which is invented, named after a book, Al-Jabr, Al-Hisab, etc., which I don't remember the full title, written by Al-Khwarizmi, after whom algorithms are named. And he was actually trying to understand the work of famous ancient Indian mathematician, Bhaskaracharya, who wrote a book called Lilavati, and which was on algebra. And it is about manipulating symbols to solve problems. So instead of numbers, we use symbols, and then later on we find the values of the symbols which will solve the problem for us. So this was algebra. The geometric
one of the interesting problem that I recall, for example, in Lilavati of Bhaskaracharya is something very simple. It says that there was a woman who got a certain number of flowers and then she was about to offer it to Lord Shiva.
Right.
But on the way, she saw Ganesha and then she gave half of that flower to the Ganesha, and then she walked further and then she saw Vishnu, and whatever that was remaining, half of it to Vishnu, and finally she gave 3 flowers to Shiva. So how much flower she plucked?
Right.
That's a kind of question. I mean, you solve this by...
Yeah, so you put a variable and then you can use it to solve. Though of course this has elegant solutions without using algebra, but the algebra solution is very simple.
The Lilavati actually starts with this kind of simple sums and then progresses to slightly complex sums. Yeah.
Yes. So on the other side, the geometry school, of course, traditionally we learned that it was done by the Greeks, but there were contributions from China, India, and so on. And in the work of the famous French mathematician René Descartes, the idea was introduced of putting coordinates in geometry. And so that gave the idea of coordinate geometry. And you can say that algebraic geometry is the modern avatar of what we study in high school, which is called coordinate geometry.
Okay. So generally geometry is something that we study as properties of circle, properties of lines. like in a sense Euclid kind of stuff.
Yeah.
And then we go into this graph paper, XY coordinates and coordinates.
Right.
You are saying that algebraic geometry is a modern avatar of coordinate geometry.
Coordinate geometry.
So, where is, maybe some simple example of a coordinate geometry?
One could look for solutions of, say, conic equations, parabolas, hyperbolas. So this is nowadays studied at a high school level. And we know that such things arise. For example, they were studied extensively for the orbits of planets, for the movement of comets and things like that. So that is where they started gaining interest. And algebraic geometry.
So something like, for example, x square plus y square equal to c would give me one circle.
Yeah.
Right?
You could take ax square plus by square equal to c, then you get ellipse. Or x square is equal to y, you get a parabola. X square equal to y square, you get hyperbola.
So this formulas look like algebra.
That's right.
But actually they are describing some geometric figures.
That's right.
That's a kind of connection that comes in coordinate
in coordinate geometry. So depending on which one you feel more comfortable with, either you look at the algebra and you do the manipulations in the algebra and you try to understand the geometric meaning of those, or you might be starting from the geometry and get an idea from geometry and then use that to solve the algebra problem.
So something like, for example, if there is a circle and I say that there is a line that is going through that circle and I want to know what are these 2 points where the line intersects.
That would involve solving these two equations at the same time, what we call simultaneous solutions.
Simultaneous equation, and then wherever the value falls in, I mean, you say that these are the 2 points, right? This x1, y1 and x2, y2 are the 2 points which are in both this and that, and satisfy both equations. That's how, I mean, you solve the...
So what Descartes discovered, and which is later on carried forward by people like Newton and so on, is that with algebra used within geometry, a lot more problems can be solved with algebraic tricks, calculus, and so on, which are much harder to solve if you just try to approach them purely from geometry point of view. Similarly, later on with algebraic geometry, we have seen that there are problems in algebra which are hard, but when you have a good geometric insight, that allows you to solve the algebra problem also.
Okay. So you mean to say that if you have an algebraic problem, I mean, if you imagine it as some kind of a shape, then your solution is much easier.
So if you want, I can give you this example which I was just telling you, that some of my friends asked me about this 1729, which is supposed to be sum of two cubes in two different ways. And they said, are there any other such numbers? And in algebraic geometry, we would think of the problem sum of two cubes and sum of two other cubes as giving an equation with 4 variables, x cube plus y cube equal to z cube plus t cube. So this we think of as a surface, and we can find a line in the surface, and by cutting that line, we can unfold the surface, and using that, we can write down many solutions. So this...
Okay, for this equation, a cube plus b cube equal to c cube plus d cube, what are all the A, B, C, D's where this will stand?
Right.
You can, if you do an algebraic thing, it may be very, very difficult, but whereas if you have a geometric
intuition, you get the idea how to write the solutions.
Okay. That's the 1729 is related to Ramanujam, right?
That's right.
So what is it actually?
So it's the smallest number, which is the sum of two cubes in two different ways. And when we say two cubes, we are looking for integer solutions. So that is another part of algebraic geometry today, which has become of lot of interest, is to find solutions of these equations in integers. And this is called sometimes Diophantine geometry because it was studied by Diophantus earlier. And there were a lot of contributions again from the work in Indian school. People like Bhaskara and Brahmagupta, they solved the equation x square minus something times y square equal to 1. So a very difficult problem of this kind is something like x square minus 67 y square equal to 1. And the solution is quite difficult to find, but they had found the solution very...
I mean, in modern mathematics, it's called a Pell's equation, but whereas it was solved much earlier by Brahmagupta.
So of course, if we just see it from geometry, it's a hyperbola. But then we are interested in the solutions with rational or integer coefficients. So that makes it more difficult.
Very, very interesting, and we have understood slightly what this animal called as algebraic geometry. We'll continue this conversation We'll take a very short break. Keep watching Eureka. We are going to continue this conversation and we are going to go into very interesting areas. A student whom he taught came back and told that if I have to tell you what I am working on, I have to shoot you. Well, we are going to watch, we can going to listen why this is so. After the break, keep watching Eureka.
यूपीआई ने बनाया जीवन आसान, लेकिन ये कितना है सुरक्षित, इसका कैसे करते हैं इस्तेमाल, जानने के लिए मेरे साथ देखिए अर्थनीति शनिवार शाम 7:30 बजे सिर्फ राज्यसभा टेलीविजन पर।
Welcome back to Eureka. We are having a very interesting, very informative conversation with Dr. Kapil Paranjape. He is the Professor of Mathematics at the Department of Mathematical Sciences at Indian Institute of Science Education Research, Mohali. Before the break, we sort of understood what this new animal called algebraic geometry. And quite obviously, this is not a very old discipline, right? So, roughly when it came into existence?
So, in some sense it is old.
Yeah.
In the sense of coordinate geometry. But the modern version, I suppose, starts with the work of, we normally say Italian school, which was just before the 1900s. But the formalization was done in the work of people like Hilbert, Emmy Noether. They were the initiators of what today we might call algebraic geometry. Of course, it has grown all over the world. There's many Russians, many French, and big school in Bombay, in Tata Institute, has made a lot of contributions. So these are some of course, America.
Yeah,
so these are some of the areas.
So right now, world over, I mean, this is a very
it's a very active area of research.
So what are the kinds of issues? What are the kinds of problems that today the people working in algebraic geometry are looking at? What are the kind of issues, if one can say so?
Yeah. So the work of the Italian school and of before that a little bit kind of has exposed fully our understanding of what we might say curves and surfaces. But so I'll come back to this point a little bit, that we understand curves and surfaces. So one of the studies is to try to study higher dimensions. So so during my postdoctoral time, I went for a school called higher dimensional geometry. That means 3 and 4 and so on. But at the same time, when I say that we understand the solutions of curves and surfaces, it is more from the geometric side. But when you try to do the algebra, it is still, or the arithmetic, trying to find rational solutions, those problems are still hard. So a lot of work went into studying the solutions of curves over what in the Diophantine case of number, where the solutions are like 1729, we are looking for integer solutions. And it is those problems which then became like Fermat's last theorem problem was solved. So that is a number theory problem. It's just a curve, but we don't understand the integer solutions so well. So that took until 1995 to solve. But from the point of view of geometry, it was reasonably well understood all the way back into 1950s or so. So each time, the questions we ask become harder. The object is the same, but we start asking more and more difficult questions because we are interested in finding number theory solutions and so on. So this is one way in which the subject becomes harder. Other way is the dimension increases.
So dimension increases means, suppose if I take a parabola, it's a 2-dimension. Suppose if I rotate it, then the surface that I get is a 3-dimensional.
Well, that's the what we call embedded dimension. So the parabola is embedded in 2 dimensions, but it itself is just a curve. So similarly, we would have surfaces, then we can have 3 dimensions, 4 dimensions. And as you said, famous geometer Riemann has said that how do I imagine, and students ask me this, how do I imagine n dimensions? So you take n minus 1 dimensions and you move it and the points as they move make an n-dimensional space. So, so each dimension can be seen as just moving the one of the previous dimension, and one gets intuition slowly. The people recently I read an article that in biology they have said that we can imagine 11 dimensions or more. So I don't know. Certainly geometers can.
Yeah, that's a very interesting point. So now let's shift to some other area. I mean, the kind of teaser that I put before this break. One of the student that in a class who studied, I mean, where you taught, after you met him after some time, I mean, he told that I should shoot you if I have to tell you what I'm working on. What is?
So it is very interesting now that the subject has grown, and there are applications which are in cryptography, and of course cryptography applications have military applications, and so one of the biggest employers of algebraic number theory and algebraic geometry people in the United States is their National Security Agency. So this student, after graduating from his PhD, started working for the US National Security Agency. This was when I was teaching in Caltech.
Okay.
And so I asked him, what is the research you're doing? And he said, if I tell you, I'll have to kill you. So that was half
And of
joking.
course, you didn't ask him.
No, it was half
Obviously.
joking, of course.
Yeah. I think we will take a very short break here, and then we will talk about what are the applications of algebraic geometry. Of course, generating new knowledge, understanding mathematics is very interesting, but is there any real life application? After the break, we are going to discuss this. Keep watching Eureka. Welcome back to Eureka. We are having a very interesting, very insightful conversation with Dr. Kapil Paranjape. He is a professor of mathematics in the Department of Mathematical Sciences at Indian Institute of Science Education Research, Mohali, Chandigarh. Before the break, we were talking about what is algebraic geometry. Maybe one of the uses is cryptography, you said. Why in cryptography? People thought that cryptography people were using something like number theory, like prime numbers. That is the kind of thing that has been in vogue.
So when people first started working with cryptographic systems, I think they were coming from computer science. They used combinatorial things, permutations, combinations, things like that. And then slowly they got interested in using number theoretic methods. But then they found that there is a limitation of the number theory methods, which is that as you want to make the cryptographic system more complicated, the prime numbers you have to deal with are very large. For example, a typical one which is now considered safe uses a prime number which has 300 digits.
300 digits.
So,
well, okay. Okay.
So
you can't even find out what number it would be. I mean, you can't even pronounce it, right?
Right. So of course, then one has to have special techniques to deal with this, and the computer scientists had developed these techniques. But over a period of time, when people realized that we also need to make it for processors like on phones and so on, which are small, which have less memory, less power. So they wanted to make systems which are small, but which are still unbreakable. And there somehow they were able to find that using algebraic geometry, they can reduce the size of the numbers you have to deal with.
Okay.
And so what is called nowadays elliptic curve crypto systems came into vogue. And since about 2000, it is quite a bit used. lot of the cell phone technology, a lot of our commercial transactions now are encrypted using what is called elliptic curve cryptography, and even signature algorithm exists, which is called the digital
So when you take your WhatsApp and you agree that I want my messages encrypted, when you make the choice, you are kind of using one of these kind of
It's possible. I am not 100% certain about WhatsApp, but certainly it is used in a large number of systems.
Yeah, so one uses cryptography. Okay. What other kinds of real world use are there for algebraic geometry?
So another use which I've heard of is that, which I had discussions with somebody. So there is a part of algebraic geometry which is more algebra, which is analysis of functions of many variables.
Okay.
And trying to simplify them, trying to simplify structures which we call matrices over these large number of variables. And this work is motivated from the geometry side, but the algebra has to be worked out. How do I simplify these matrices? With the traveling salesman problem, we do that same thing over integers, but here we want to do it with functions of many variables.
Okay.
And trying to simplify these is a critical problem for what is called optimal control.
Okay.
And so this is used in robotics and factories and so on, other places where you want to optimize the number of controls so you want to reduce the number of controls that you're going to use, because each control costs you money. So you want to have fewer controls and try to control the system with less controls. This kind of problem is being studied using algebraic geometry, and some of the key developments in 2 and 3 variables was done by Indian mathematicians, but the general problem was solved by Quillen and Suslin, but the original contributions which they built on were done by Seshadri and Pauman Murthy.
Okay, very, that's interesting. In a sense that foundations were laid, but of course it's an international effort.
Right.
So others also pitched in
Right.
subsequently. The other one area that you talked about is of course in things like control, right? Artificial intelligence, is there use that people are thinking of?
So in the sense of robotics, yes. So optimal control goes into robotics. Again, for the same reasons, we would like to minimize the number of controls. So one of my friends gave a talk on how you can ideally control a video camera, CCTV, by using the minimal number of controls, and you can show using something called quaternions that the number of controls can be limited to 3.
Okay, I see.
So
So,
these are
I
some
mean,
applications, but this, of course, quaternions was known for many years, so it's not something recently developed in algebraic geometry.
Okay, that's interesting. Let's move to a different area. I mean, most of us, when we hear something like mathematics, the first emotion that comes to us is fear or apprehension.
Right,
Many of us have a maths phobia,
that's right.
right? So, why do you think it exists?
So the way I see it, there are 2 sides to the phobia. One is that when we deal with mathematics, we are actually developing new concepts. So the way I tell my students is that we are building a bigger vocabulary. So of course, unless you become familiar, suppose I tell you to think about a whale and you have never seen a whale, it will be frightening because I'll tell you only about the weight and things like that. So similarly in mathematics, we might be talking to you about something which you have not really worked with, then it is scary. So the other side of mathematics is working with formulae. And there are people who have problems with the written word, with formulae and so on. And that phobia is, they have to just work with it, and you get familiar. People are afraid of the computer, but once they use it enough, nowadays people don't think that they are doing anything great by using email. But certainly 15 years ago, I know people who would say, I'm scared of doing email even. So I think what happens is there it's more familiarity of using it. But as far as the vocabulary is concerned, you have to, after using it, you have to see it from all sides. It's like the elephant. You see it from many sides, then you get familiar, then you feel, okay, I know that if I stay on this side of the elephant, it will not trample me.
Okay.
So I think that is one aspect, that we have to get familiar with the concepts.
Yeah, that's it. Another thing that people generally think is that, okay, for physics or chemistry, or if I want to become an engineer, I need mathematics. But if I'm going to take botany, zoology, life sciences, I'm going to do microbiology.
Right.
I don't need maths at all.
Yeah, of course in IISER we specifically in our institute we take students from all sides. The class I'm now teaching has about 50% who have not done maths in 11th and 12th. And what I try to emphasize is that we are building concepts from arithmetic which I already learnt in high school. But the part which I think needs to be emphasized for them is that there are aspects of mathematics which are impinging their life. So one of the big studies in recent times done by the American Statistical Association said that one of the reasons why certain experiments are not repeatable is because the statistical analysis of those experiments was not done correctly.
Okay.
So what there is, it's not that the experiment was done wrong, but the analysis was wrong, so the results are not actually supported by the way the data should be analyzed.
Okay.
So actually when we do pharmaceutical experiments and so on, we have to actually learn enough statistics so that we can correctly predict that the medicine actually will be effective. And last year when I taught a course in statistics, I did point out to the students that one can fudge the test by carefully, managing the statistics. And obviously when you want to do it an honest experiment, you want to know the statistics well enough to avoid such pitfalls.
Okay. So in a sense that in today's world, there are almost no area which is untouched by mathematics?
I would say that it's true, and I don't want to be frightening in that sense, but it is the same as saying that there is no area which is untouched by language.
Yeah.
If you limit yourself to the language which you learned in school, you will not be able to discuss higher level, more complicated things. When we discuss economics, we want to understand growth. So I'm writing an article on growth. And it's a very important thing. Why are we afraid of China? Not because our growth is bad, but because their growth is better. So you have to understand these things, and they are given in terms of numbers.
Yeah.
And so ultimately we have to be able to build our vocabulary and understand the concept of growth in a conceptual way as well as in the mathematical
So it's in something like, for example, learning a language. In a sense, maths is another kind of language.
It's a bigger language.
It's a bigger language. And to the extent that you are familiar with it, to that extent that you will be able to articulate, understand, and use it, right?
Yes.
So there is no need to fear. Like you don't fear a new language. A new language which you don't know is, of course, is not something that you are familiar with, but it's not something to be feared.
Yeah, that is one way to see it. Also, when you suppose I go to a different place, even in your own language, you might find something which is new. So you go and you are given a new fruit. You have to taste it. And when you taste it, you may enjoy it, and you may find that yes, it is something which is worth doing. And so
That's been a very, very wonderful conversation. We had a very excellent conversation with Dr. Kapil Paranjape. Thank you for being with us in the show. Keep watching Eureka. We'll come back with another interesting conversation next week, same time.